Welcome to the first step of the course, Introductory Physics. In this step we will show the motion of an object at constant velocity. Motion at constant velocity can be described by Newton's first and second law of motion. Newton's second law can be described by two equations. The first one is that the final position is equal to its initial position plus a term of the average velocity and the change in time. And the second equation shows that the final velocity is equal to the initial velocity and the net force times the change in time divided by the mass of the object. With the two equations, we can describe the motion of every object. Newton's first law is a special case of the second law, when the net force of the system is zero. So we can cross this term here, and we see that the initial velocity is equal to the final velocity. This means the system has a constant velocity. Therefore, if no net force acts upon a system, the system will remain at rest or will move at constant velocity. As an example for this lab, the motion of a bike will be analyzed and compared with a computer simulation. The bike was accelerated and then the feet were removed from the pedals as shown here. For the analysis of the video, we can use the software tracker. The origin of the coordinate system was chosen as the center of the gear wheel, because the gear wheel is a fixed point and is also small enough to find an accurate point. As a length scale, the diameter of the wheel is chosen. The wheel has a diameter of 26 inch or 0.66 meter. So let's watch the video. We choose the positive x-axis oriented in the same direction as the bike, and therefore the curve starts at the origin and increases linear with time. If we flip the orientation of the axis, the displacement would decrease with time. So the average velocity would be negative. But if we take the magnitude of the average velocity, it does not matter in which orientation we will choose the axis. The motion of the bike was simulated with the software VPython. We apply Newton's first law, where the force term is zero, and using an average velocity of 2.374 meters per second. If we run the program, we see on the one window the bike, and on the other window the linear increase of the displacement with time. Both curves are plotted in the same graph. It is shown that the experimental data fit well with the simulation, except in the middle part. Because the velocity is not constant, we have additional forces: drag forces, friction forces, and forces through non-uniform ground acting on the system. Let's see which is the major reason for the middle part. So we can go through the explanations. First, the drag force, which is equal to the velocity and a constant b, and the force goes into the opposite direction than the velocity. If we are taking into account the equation for Newton's second law, we see that the final velocity is lower than the initial velocity, and therefore the experimental curve should be below the model curve. This is not the case, and therefore we can exclude drag forces. The second explanation might be kinetic friction force. The kinetic friction force is equal to the coefficient of friction and the weight mg. The friction force is also in the opposite direction, and therefore the final velocity is less than the initial velocity. We can also exclude friction forces. The last possible explanation is that the walkway is not uniform. There is an entrance which is in general a little bit deeper, and therefore on the one side it is going down and on the other side it is going up. We can build two triangles with angle theta and gravitational force in y direction. Now we can calculate the distance with SOHCAHTOA. But what is SOHCAHTOA? SOHCAHTOA is a geometric trick to remember sine, cosine and tangent. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So we take sine, and for going down the force is plus mg sine theta, and for going up the force is minus mg sine theta. Therefore the final velocity is larger at the beginning and less at the end, which fits very well with our experiment data. Even though drag force and friction force acting on the system, the non-uniform ground is the reason for the difference in the middle part. This was the first step of introductory physics. Thank you for watching this video.